Actually, this, remember that this is 2D only, right? Because this conformal mapping kind of thing in the complex domain, so the complex domain is 2D. We have quaternions in 4, but it's not that useful. So, but it's exact, right? We did not have any assumptions here. I mean, from potential flow, we did not assume anything else, and we got it exactly. The other method is method of singularities. So this is your shape. You replace your shape with a distribution of singularities of unknown strength. Maybe vortices, sources sink, and whatever. Okay. So gamma as a function of x and y, and this is unknown. And you use your boundary conditions to determine the gammas. Obviously, this is applicable to 3D because you can also replace your wings. So this is finite wings, that's fine. Actually, the lifting line theory is like this. Finite wing, sometimes even fuselage. But it's approximate in the sense that you we usually approximate our shape by very thin stuff. And even if not, we cannot cover all, we have to discretize. So these are the two things. We had enough meat here, we will go there. So this is from here. The thin airfoil theory emerged. Sometimes it's called skeleton theory. Sometimes it's called theory of what? Lifting vortex sheet. This is our next topic. So this is Prandtl. It's Prandtl and his students. These are students of Prandtl. Birnbaum, Ackermann. Prandtl almost did everything to it. He's the father of aerodynamics. He's steady, unsteady, Prandtl-Meyer fan, almost everything, even turbulence. Birnbaum and Ackermann, 1923, and also Glauert, his Prandtl-Glauert, his student, and Blasius, skin friction drag, his student. Glauert, 1926. So they developed what we know here in the West as the thin airfoil theory. I guess they called it in Germany what maybe translated as skeleton theory, because it's the skeleton of your airfoil. So about 5 minutes you can develop, Let's look at that. Let's look at the simplest form of the thin airfoil theory. We have a flat plate because we already know the solution of a flat plate. So we said we're gonna replace this whole thing with a singularity. So let's do the simplest thing. What's the simplest thing? Just put a single one of these. So I will put a single gamma. Okay? First of all, where should I locate this gamma? Well, for a flat plate, I know the distribution already. So I can, the distribution of the velocity field, the pressure field, I know everything over the flat plate, so I can get the circulation and get the resultant. The resultant is the point called center of pressure. And for a flat plate, let me give it to you here. So this is the pressure distribution, by the way, as a function of x on the plate. I mean, you can derive it from the tools that we had so far. You have everything, right? We were just waiting for the amount of gamma, we got gamma, so you can do whatever you like. So this is the flow field. It's 2 sine 2 alpha square root of c over 2 minus x, c over 2 plus x. So this is the pressure distribution. Do we have to? Or not? Yeah, we have to. So this is the pressure distribution. So you can get the resultant of this pressure distribution, gives you the center of pressure. This is at quarter chord. Okay. Flat plate at any angle of attack, it's at quarter chord, which is the same as the neutral point. So the moment at this point does not change at the angle of attack, and it's the moment 0. So, okay, if this is the center of pressure, it's very legitimate to put this guy at the quarter chord, okay? So we're going to put it at the quarter chord. Okay, so whenever you have a flow coming to your flat plate, I will replace my flat plate just all the way and put this here. Very simple. How can I determine my gamma? We need to use our boundary conditions. What are our boundary conditions? The boundary condition is that the flow normal to the surface is 0, right? The flow doesn't penetrate the surface. The flow comes and flows along the surface, right? Actually, it's called like this, no penetration boundary condition, okay? Sometimes it's called kinematic flow condition. Okay, because I have, okay, the thing is, this no penetration boundary condition has to be satisfied at all points. So ideally I have infinite number of equations. The normal velocity at this point is 0, at the point 0, at this point is 0, all points is 0, okay? But I need only one of them, because I have only one unknown here, okay? So which equation should I pick? What is the most appropriate equation should I pick? This is the point. In other words, what is the point at which if I dictate that the flow normal is 0, give me a good value for gamma? Well, we can do this here because I know what's the correct gamma, right? I know what's the correct gamma, so here is the flow. The flow due to this guy, this is u infinity, so I have u infinity here. This is alpha, so this is the normal component, u infinity sine alpha, coming from the flow field. So I need u infinity sine alpha due to gamma coming from there, and that's it, right? So u infinity sine alpha coming from gamma. So it's gamma over 2 pi, some distance here, okay? This distance is the distance between the quarter chord and this point. And in order for this to give you the correct gamma that we already know for a flat plate, this has to be what? Remember it was what? 4 pi or pi u infinity sine alpha, right? So this has to be c over 2. This has to be c over 2, which means that this point is what? This point is what? The 3/4 chord point. So this is actually something called Pistolesi theorem. Is that if you want to write your left, if you have a varying angle of attack, if I have the whole section has one angle of attack, so the whole section is rigid, has one angle of attack, the CL is 2 pi alpha or 2 pi sine alpha, because it's 1 alpha. But if I have some flexible chord, or if I have rotationality everywhere, so that I have local angle of attack changing from one point to another, and if I want to use this relation, this global relation, as if I have a single angle of attack, is there a only one point that matters? It's a very big question, and the answer is yes, it's the 3/4 chord point. So you need to only know the angle of attack at the 3/4 chord point. Just measure this, get the left information. This relation is very useful.
Wait, shouldn't the no penetration condition apply anywhere, not just in?
All the way, but we have a very, very idealized thing that I put only one vortex. The very next step is to put infinite number of vortices and satisfy it everywhere. We will do it next time. This is the thing for you. But this was an introduction. See you next time, and the homework is due next time.